next session on Advanced ANSYS Workbench tutorials. In this session, we will analyze the globe valve for its steady-state thermal analysis. We will start by double-clicking on steady-state thermal module. We'll first go to engineering data and double-click. I will analyze for 3 different materials. So first we'll go to engineering data sources, click on general materials, choose stainless steel as one of the material. Then again go back to engineering data sources, and here I'm going to create 2 more material. One is brass, for which we will select isotropic thermal conductivity. The value is 115. Then we'll create the next material, which is bronze, for which the isotropic thermal conductivity is 208 watt per meter degree Celsius. Then we go to project and update project. All the 3 materials have got added. So we'll go to geometry and right click. Import the geometry of the globe valve. Then I'll go to model and double click. We'll first go to geometry here, select the globe valve and change the material to stainless steel first. We'll go to mesh. I'm using the default size of the mesh and I'll generate. Next I'll go to steady state thermal. I'll right click here and insert temperature. Now on the inner side you can have a temperature which can range from minus 254 degrees Celsius to 593 degrees Celsius. So first we will take up a negative temperature inside. Now if it is a high pressure globe valve, then we can have the temperature ranging from minus 40 to 550 degrees Celsius. So suppose if it's a high pressure valve, so we will select the inner face and click here. I will give this temperature as say minus 35 degrees Celsius, and on the outer side I am going to give room temperature. So I will right click here and insert temperature on the outer surface. And then I click here. Outer temperature is say 22 degrees Celsius itself. Also I am going to insert convection on the outer surface. Click here. The value of film coefficient I am going to give in watt per meter square degree Celsius. So I'll change the unit here, and this is approximately 5 to 25 watt per meter square Kelvin for air. So I will give this value as say 20. Ambient temperature is 22. That's what we have taken. Now I'll go to solution, right click, insert thermal temperature. I will insert thermal total heat flux. If you want, you can also have a directional heat flux over the body along the x-axis. Then I'll go to solution and solve. So let's see the temperature. You can see over here maximum is 25.816 degrees Celsius, which is in red over here, and minimum is minus 35, which is the value we have given. Then we'll see the total heat flux. You can see the highest value is 4.5476 watt per meter square. This is all over the body. And if you want to see along the x-axis, maximum is 3.92 into 10 raised to 5 watt per meter square. This is when we have stainless steel as the material. Now, if you change this material to brass and solve once again, if you click on the temperature, you can see the variation of temperature for brass, maximum being 25 on this outer zone, minimum is minus 35 as we have given. Total heat flux, you can see 3.46 watt per meter square is the maximum value. Minimum is 0.3574. Directional heat flux also you can check. The value is higher as compared to stainless steel. It is 2.99 into 10 raised to 6 watt per meter square. Then we will change this material to bronze and we will solve once again. Let's click on temperature. You can see this variation. Total heat flux is something which is varying for each material. Here it is 6.26 into 10 raised to 6 watt per meter square highest, and directional is 5.4 into 10 raised to 6 watt per meter square maximum. Again, it is more as compared to stainless steel and brass. That's because the value of K is different for all of them. Now what we'll do is we will make a small change, that is this internal temperature we took as minus 35, which can range from minus 40 as I told you to 550. So let's change this value to say 450 degrees Celsius. We'll go to solution and we'll solve. Now temperature 2 is something which I'm not going to change because this is the outer temperature. Convection also we don't need to change anything here. So let's solve and see for bronze what we get. This time we'll go reverse. First we'll solve for bronze, then brass and then stainless steel. So let's see the temperature here. 450 is what we have given as the maximum. It's red inside. And outside the temperature is minus 6.6 degrees Celsius. You can see here. You can go to probe and you can check. Actually, it is not minus 6. It is showing 22 degrees Celsius itself. But if you read here, it is showing minus 6. It could be at some place on this globe ball where it is minus 6, but it is not. It is actually 22 degrees Celsius. Then we'll go for total heat flux. Maximum is 4.7 into 10 raised to 7 watt per meter square. For bronze, given this boundary condition now. The boundary condition has changed. You need to make a note of it. Initially, the temperature inside was negative. Currently, it is positive. Then we have the directional heat flux. You can see here 4.19 into 10 raised to 7 watt per meter square is the highest value of directional heat flux. In the first case, what we had was the heat outside was more. It was 22. Inside it was minus 35. Currently, inside it is 450, very hot. And outside it is cold, 22 degrees Celsius. And as you know, heat travels from higher temperature towards the lower temperature. So we are actually trying to cool the surface because of the air. And in the first case, internally it was cold and outside it was hot. So the heat was entering that globe ball. Now let's change this material to brass and let's see the value. Go to solution and solve every time to get the solution. If you click on temperature, you can see the same variation of temperature like in the first case. The values may change a bit. Then we have total heat flux. You can read this value is 2.6006 into 10 raised to 7 watt per meter square maximum. Minimum is 2.68 watt per meter square. This is all over the body. Then we have directional heat flux. The maximum value is 2.32 into 10 raised to 7 watt per meter square. Now obviously this is less as compared to bronze. Then we will change this material finally to stainless steel such that we are able to draw a conclusion between the three materials. solve once again. We'll go to temperature, then we'll go to total heat flux. Maximum value is what we have to read for the total heat flux. For stainless steel, you can see a variation clearly for three materials. Here it is 3.414 into 10 raised to 6 watt per meter square. Directional heat flux, you can see it is 3.04 into 10 raised to 6 watt per meter square. If you see here, for stainless steel, the value of thermal conductivity is 15.1. For bronze, it is 208, and for brass, it is 115. So obviously, when you are studying the heat flux, it will be more for bronze, then it will be for brass, lesser than that, and then finally, or the least will be stainless steel. So more heat will be lost or transferred in case of bronze. That means the heat flux will be more for bronze as compared to the other two materials. But that does not justify the use of the material. You need to see the other parameters as well. For example, cost or the weight of the material, if it is anti-corrosive or not, will there be any oxidation because of the use of a particular material and some chemicals around it or inside it. So you will have to check various parameters and not only the thermal aspect of it always. Overall, you will have to decide which material for the globe wall you're going to choose. So with this, I end this session. I hope you have understood the analysis. If you have any doubt, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.